Welcome to my review of Chapter 7 of the Top-Down Network Design textbook. In this chapter, we're looking at selecting switching and routing protocols. So this is always really good, um, though I don't quite think this small of a chapter could really go that in depth with routing protocols or switching protocols, but we're going to see. So switching and routing choices. For switching, at least if we're looking at layer 2 switching, it's a transparent bridge switching. We have multi-layer switches, layers 2 and layer 3. We have some techniques that we could put in place, things such as STP or spanning tree protocol, or the variations of spanning tree protocol, as well as some VLAN type technology. What's really funny is, I guess you can call those choices, but I mean, those are just basic features that are in a enterprise class switch. Routing, we can have a static or dynamic routing. You can have your own static routes that you, the network admin, happens to design. Normally, if we're talking dynamic routing, we're talking normally a distance vector or link state. Those are two. There are some hybrids. Interior or exterior gateway. A great example is like BGP. There is a interior gateway BGP called IBGP, and there is an exterior gateway protocol for BGP called eBGP. BGP is typically the routing protocol that the internet uses, so you can actually implement BGP on smaller networks, but there's some complexity to that. I'm actually going to not touch too much on that. If you want to know more about BGP, review my videos on BGP. Going forth, we have to understand how we're going to select the appropriate protocols. Normally, we'd be looking at things like budget, traffic characteristics, resource utilization, resource being bandwidth, but the switches and the routers both have finite resources. They both have limited memory and limited processing power. Actually, this is kind of important because I just realized this the other day. I have a Sonic wall, which is owned by Dell, and I pay for a 200 megabit connection at my house. And my Sonic wall TZ215, when I do a speed test, it gets to about 145, 150 megabits per second, and then stops. And I'm like, okay, that's kind of weird. Maybe my cable provider is not giving me the appropriate bandwidth. So first we called them and we verified. And turns out it actually was my router. And it had never dawned on me to check CPU usage. Turns out when I did a speed test, at about 145 megs, the controlling plane and memory for my Sonic wall were at 100%. So the Sonic wall device could not process more traffic. It was as fast as it could go. Even though on that particular model, I had gigabit in and gigabit out, it didn't mean that the processor that was in the device was capable of handling the traffic going through it. So that was kind of interesting. Other characteristics could be the number of peers, the number of technologies, what type of technology we're going to be working with. Are we working with VPNs? Are we working with site to site? Are we working with mobile clients? There's a lot of things that are there. One of the big things is capability, scalability, and adaptability. If I get a particular design and I want to be able to quickly change or add things to it, can my protocols keep up with that? For example, if we're doing everything statically, trying to make quick changes, static is not going to work. So the capabilities of scalability have to be there. One of the last big things is This whole support for authentication, I'm sorry, I disagree with that. There needs to be full-fledged security support, not just authentication. We're talking at least AAA. Authentication, authorization, accountability. We need to be able to see what's happening, who's doing it, or who's not supposed to be doing it, all of that good stuff. We need to be able to verify the routing protocols have the appropriate authentication factors, that we're only partnering or peering with our adjacent neighbors that we approve of. No, well, not really no. We should have a mechanism in place so that we only accept maybe route changes from known devices or known paths, so that we will have no poison routing or poison switching or poisoning of our MAC tables. Sorry, I just did a video on ethical hacking where we were doing art poisoning. So, yeah. So we have to make a few decisions. We have to keep goals, the mission statement, budget kind of in mind. We have to understand the technologies that we're working with. For example, if we're doing all Juniper, can we do EIGRP? Well, no. EIGRP is Cisco proprietary. So we have to keep in mind, what are we going to be doing? We have to have some change management plans, some contingency plans, some type of decision table is always really good. That way we can discuss what is the appropriate protocol. So IGRP, well, this is what's really weird. I've seen IGRP displayed as the lesser of EIGRP, but I've also seen IGRP as interior gateway routing protocols, more as a generic name for interior protocols or routing protocols. So I've also seen it as IRP. So I just want to put that out there. So BGP, OSPF, EIGRP, those are going to be some common routing protocols. Normally BGP not so much, unless you have a large network. OSPF and EIGRP are pretty common. So let's get back into our switching. So the nice thing here is, what's the purpose of a switch? Forwarding frames, normally transparently. They need to learn the appropriate MAC addresses coming on which ports so they can build a MAC address table, also called I always forget the appropriate, I always forget, I keep wanting to call it CAN, C-A-N, but it's really CAM, C-A-M. Basically, we're looking at the forwarding information base, the FIB, which is also known as the forwarding table, and CAM table. It is the most commonly used in network bridging and routing, and similar functions to a popular interface. It's very similar to a dynamic table that maps MAC addresses to ports. So MAC address table is just one of them. Also, when we're dealing with switching, we have to talk about security and proper resource management so that we're not getting floods of frames. For example, unicast addresses that haven't been learned, or broadcast addresses where we have bridging loops. We should have filters in place so we can filter frames from going out the incorrect ports. We also have to be careful with flooding broadcasts and flooding multicasts. Again, a big part of this goes back to proper design, proper layout of our switches and our switch network. That way we can put certain features into place that help prevent broadcast flooding. There's lots of features that are built into switches that people don't realize that are there, like stateful frame inspection, or SPI, or STP, or variation versions of STP. Switches are pretty powerful as long as you understand the technology that they're using. A switching table on a bridge could be as simple as this: MAC address tied to what port. Cisco spanning tree, or again STP. There are several versions. There's port fast and uplink fast and backbone fast. You can actually have unidirectional or loop guards. Again, there are so many different types when it comes to spanning tree. Spanning tree is fairly simple until you get into like the MSTP or the multi-state spanning tree protocols. Those get pretty complex, but again, not super hard. Again, the whole redundant link for scalability is important, but at the same time, also understanding how we do our STP. That's also extremely important because you can actually start blocking connections or turning off links with STP if you're not laying out your network correctly. Normally people turn STP on if they even turn it on and then they walk away, but you kind of have to understand how STP works so that you don't start disabling links that are important. So be careful when it comes to STP. Don't just turn it on and walk away. Make sure you understand what links are going down and understand why. Other things when we're dealing with protocols for switching, we're talking ISL or inner switch links. Normally they're going to be tagged. In a non-Cisco switch, they normally don't call them VLANs, they call them tagging. And basically you have to tag the item coming in on that port, what VLAN you are. I was programming a Netgear switch, and we set it up at the appropriate 4 VLANs that we needed. VLANs 4, 5, 6, and 7. But the interesting thing was, on the Cisco switch, we called it VLAN 7. On the Netgear switch, we actually had to create VLAN 7, but we had to tag that port, so any frame coming in on that port would be tagged VLAN 7. We have a few other types of protocols. We have the IEEE 802.1q, which is a tagging protocol, which is non-Cisco proprietary. 802.1q is a pretty common one. Normally when I teach switching and or like CCNP level switching courses, I'm teaching 802.1q. We have trunking protocols for VLANs called VTP. VTP is always really good, always very dangerous, but always really good. Helps the network a lot more than people realize if implemented correctly. Moving on is our routing protocols. This is always real fun because you have to understand several things when picking out the appropriate routing protocol. They all have the same general goal, which is to share network reachability among all the routers. So that's one thing. But how efficiently do they do that is, well, different. Also, how do they do that? Again, it's going to be different. They differ in ways interior versus exterior. The metrics. How do we choose the appropriate path? That's going to be the measurements. That's metrics. Dynamic versus static versus default. Distance vector versus link state. Those are big ones. Class full versus classless. How scalable they are. All right, so realistically right now, class full probably is not even in consideration anymore. Most routing protocols, most networks that we're using nowadays are classless, hands down. So then becomes how big of a network, how small of a network, and that kind of can help start narrowing it down the appropriate protocol based off of that. So let's look at interior versus exterior routing protocols. Interior routing protocols are used within an autonomous system number, the same sphere of control, where exterior routing protocols are used between autonomous system numbers. BGP, great example. BGP uses autonomous system numbers. So the next common question is, what is an autonomous system number? General two definitions is a set of routers that present a common routing policy to the inner network, or a network or set of networks that are under the administrative control of a single entity. That's why I say sphere of control. For example, Cox, they control all of the routers in their network. That's probably one sphere of control. Comcast. They probably have, again, their own autonomous system number. They are not the same as Cox. Comcast and Cox, they are similar, but they're different. So they actually have probably different autonomous system numbers. So routing protocol metrics, different ways to look at how to measure. For example, bandwidth or the capacity could be reliability of the line, the delay, the load, the hop count, the costs. All of these things could be different metrics depending on the routing protocol. So which is the best path? It depends. How are we measuring? So that's where it gets a little bit more complex. So sometimes routing algorithms could be a static route, which is normally calculated beforehand. It's manually programmed. We could have a default route. If I don't know where to send something, automatically send it here. We could have Cisco's on-demand routing for a stub network using a CDP. That I don't have much experience with, but most of my experience has gone with dynamic routing protocols, distance vector or link state, or static routes, depending on again how big the network is. Static routing examples, here would actually have to say, if you want to go to this network or this network, send out this interface. Here we have IP route. If you want to, it should be source to destination. So we're looking at router A. Let me grab my pen real quick. If we want to go here with that subnet, send here. They know what's directly attached. Like router A knows about this. Router C knows about this. Router B knows about this. You only know what you're directly connected to. So here it's essentially saying if we want to connect to 192.16.50, if we want to go to that network, which is this network right here, send here. It happens to be this IP address. So basically, we're going to forward the information. I hate using so much red to router B. A default route would be send everything out to this interface. So any IP with any subnet send to this IP address here. Which, I mean, does work, but what is router B supposed to do with it? What if you're trying to get to 172.16.50.2? Does router B know about it? So that's one of the problems. We have to be a little bit more specific. So let's talk about distance vector. Routers maintain a routable table that lists known networks, their direction, also known as their vector, to each network, and the distance or the hop count to each network. Routers periodically, typically every 30 seconds, will transmit the routing table via a broadcast packet that reaches all other routers. Once all routers have all information, it's called convergence. But what happens if the network doesn't change? Is it gonna keep sending the router updates even if no changes have occurred? That's an issue with distance vector. Router updates the routing table if necessary based on received broadcasts. If it doesn't receive an updated information, it just receives the original information or old information, it still has to process that packet. So it's a waste of resources. Distance vector routing tables. Again, distance could be hop and where to send it. For example, if we're looking at the routing table for router A, 172.16.0.0 is the network. It has a distance of 0 because it knows that's a local network. It also realizes that it's going to go out port 1. If we want to go to 192.168.2.0 as the network, we're going to send it to router B. Normally it's not quite send to router B, it's going to be send to the appropriate IP address for it, but that was just more of a so that you can understand it. Link state routing protocols normally deal with sending updates only when there is a change. That way we don't have to waste resources. Routers that detect changes create a link state advertisement or LSA and sends it to its neighbors. That way, again, once everyone knows about all changes, it's converged. The neighbors propagate the change to their neighbors and so forth and so forth. The routers update their topological database if necessary. But again, this is when a change occurs, not every 30 seconds. So distance vector algorithms keeps a list of networks with next hop and distance metric. Link state algorithms keep a database of routers and links between them. The link state algorithm thinks of the inner network as a graph instead of a list. That's a big thing. When changes occur, link state algorithm applies, I can't even pronounce that, shortest path algorithm to find the shortest path between different nodes. Again, link state, the big thing here is it looks at it as a graph and updates when changes occur. Distance vector looks at it more like a list, uses next hop and distance as metrics, and updates every 30 seconds. So, how do you know when to choose which one? Distance vector you might choose it when you're choosing more of a simple or a flat topology, or maybe a hub and spoke, or if you're not really a network engineer and you're not quite familiar with how these work. But convergence time is not really that big of an issue. Link state is again a hierarchical normally used by more senior administrators, and that's when fast convergence is critical. I'm not going to argue with this slide. Both have their places. What you normally want to do is look at the characteristics of the metrics that are being used and your network and choose the appropriate routing protocol based off the metric that fits your network. Dynamic IP routing protocols, distance vector, things are going to be like RIP or EIGRP or maybe even BGP. Link state is going to be the common OSPF or ISIS. Again, normally we're looking at EIGRP versus OSPF and sometimes BGP. BGP is a hybrid distance vector, but we're not going to get too much into that. Looking at RIP, RIP is a standalone dynamic routing protocol that's really easy to configure and really easy to troubleshoot, but it's kind of crappy. I mean, if you have nothing else, RIP works, but it's classful. It doesn't really like classless networks, and the functionality is just not really there. RIP version 2 does support prefix routing and finally supported BLSM. It includes simple authentication, but that's about it. IGRP solved problems with RIP, like the whole 15 hop limitation. RIP also has that 30-second update timer, where IGRPs could use 90. EIGRP is an enhanced IGRP. It adjusts to the changes in the network quicker or very quickly. It has incremental updates, certainly are containing only changes. That way you don't have to do the entire routing table. It does update more reliably. It also updates and delivers more reliability, or more reliable, not reliability, sorry. Routers keep track of neighbor routing tables and use them as feasible successors. You learn a lot about feasible successors when you go for your CCNP route course. That's a huge topic. Same metric as IGRPs, but more granularity. You end up with a 32-bit instead of the traditional 24-bit for metrics for that. OSPF, or Open Shortest Path First. It adjusts to changes quickly, supports very large networks, does not use a lot of bandwidth, and does have authentication. OSPF is very common, so is EIGRP. Normally, OSPF metric is a single dimensionless value called cost. A network admin assigns an OSPF cost to each of the routers, and that way you can then start manipulating the cost based off of things like bandwidth. On a Cisco router, the cost of an interface defaults to 100 million, divided by the bandwidth of that interface. For example, a 100 megabit connection would have an interface cost of 1. There's actually a interface cost breakdown for OSPF metrics, which we may or may not be looking at here shortly. OSPF does connect via area border routers, or ABRs. All areas go back to area 0. Area 0 is classified as their backbone. And we have ABRs that connect the different areas back to 0. All areas connect back to 0, period. Is a link state routing protocol designed by ISO, but I think I've seen this once, and that was it. BGP allows routers and different autonomous systems to exchange routing information. That's probably because we're going to be looking at exterior BGP or BGP. It's used on the internet and large companies. Does support router aggregation. Its main metric is the length of the list of autonomous system numbers, but BGP also supports routing based on policy. So that's actually a nice brief overview of basic switching and basic routing for now. I'm going to leave you with some review questions. What are some of the options for enhancing spanning tree protocol? What is spanning tree protocol? What factors will help you decide whether distance vector or link state routing is the best for your design? What factors will help you select a specific routing protocol? And why do static and default routers still play a role in many modern network designs? That's it for this chapter. I want to thank you.